Hey guys, welcome back. SCHIZONE series episode 10. Topic today is the basics of the matrix. Simple topic, honestly. If you click this video, you probably already know A, everything I'm going to cover, and then B, more than me. So if I check the analytics and even like one person watches more than 2 minutes of this video, I'm going to be so disappointed in my audience. Anyway, so yeah, we're talking about creating matrices, populating them, manipulating them, doing some basic arithmetic on them. So should be a good, quick, short, easy video. All right. So the question of the day ultimately is, let me shrink myself down a little bit. How do we encode arrays of floats? And we're talking about double precision floats, so 8-byte floats for this whole video, so keep that in mind. So 2D array. Memory isn't 2D. On your computer, you have linear memory. You have byte 0 all the way to byte a million. Probably more than a million if you're from the current century. So the question is, how do you encode a 2D concept in a 1D architecture, I guess? And so there's two ways. There's row major ordering, which is most common by far, and then there's column major ordering, which is, pretty niche and no one uses it pretty much. That's not true. I've seen usage of this very often, actually. But basically the way it works is row major ordering, you just pull out the rows and drop them into memory. So you can see the array is 1 through 9, and so row major ordering is just 1 through 9. Column major ordering is a little bit different. It's basically you pull the columns out. So column 1, column 2, and then column 3, and drop them in one after the other. So it's pretty simple stuff, nothing advanced here. The only thing that matters is, for most operations, it doesn't matter what you use. As long as you're consistent, you can use whatever you want. So let's say you want to add two matrices. It doesn't matter. As long as they're both column major or they're both row major, your program will work. The problem arises when you have A, you're mixing and matching row major and column major, which is just not going to work. And B, if you try to use an algorithm that is designed for row major, but it's used for column major, it's not going to work, obviously. So for example, any algorithm that requires you to index into a matrix, like for example, let's say this element 2 here, that's the second element in row major ordering, but it's the fourth element in column major ordering. And so obviously your math's not going to work if it involves indexing into a matrix. So yeah, there's that. So we're going to use row major ordering just because it's most common in my experience. But again, it's pretty much it's interchangeable, and it's just a matter of the transpose. Next question is, how do we pass arrays into a function? So a couple different options here. Actually, there's infinite options, I would say. Some are good, some are bad, but they're all workable. So the first option would be, hey, let's push the entire matrix onto the stack. So drop this whole matrix, all in elements, times 8 bytes onto the stack. Hey, that would work. But you also have to pass in number of rows and columns, but yeah, you can do that. That's not a big deal. Another option might be, hey, let's put the matrix into registers. We have 14, 15 registers to use, so hey, let's just pass everything in there. You can fit a 3x3 matrix in registers, so hey, that's most of algebra. Most algebra is 3 dimensions, so hey, 3x3, that will fit. It's not good for big matrices, obviously, but hey, it would work for small ones. Option 3, hey, let's pass the first element address as a parameter, and let's also pass the number of rows and columns. That's probably the most common way to implement matrices. That's how it's done in C. That's how we're going to do it in this series. But hey, there's other ways to do it. And then lastly would be, hey, let's make a custom data structure that includes, hey, the elements, and then it also includes number of rows, number of columns, and hey, how about some other metadata as well? How about like the name of the matrix? How about like number of elements? How about the maximum value? You could include all that stuff in your data structure, right? So they're all workable options. There's many more. We're going to stick with option 3. Cool. Okay. Here's how we're going to do it. So in a function, we're going to pass in, here's a function that uses a matrix. We're going to pass in at least 3 things. That is the address of the first element, so a pointer to that double. We're going to pass in number of rows and number of columns. So here's how it's going to be. We're going to have some matrix defined in memory. Here I'm defining 6 quad words, so 8 bytes each. 1, 2, 3, 4, 5, and 6. So this is 6 8-byte double precision floats. But hey, what is that? What does that even mean? That could be referring to a 6x1 matrix. Could be a 3x2 matrix. Could be a 2x3. Could be a 1x6. It could even be a 2x2 matrix with 2 extra garbage at the end. It could even be a 1x1 matrix with a bunch of crap at the end, but you don't know. So it's all about how you're going to understand that memory. So we're going to basically have to pass into this function the address of the first element, number of rows, number of columns, and then call the function. So very simple. And some people might bring up, hey, why are we using a full 64-bit register to encode numbers like 2 and 3? It's a good point. We could compress that down to a much smaller data type. I'm not going to for this series keep things simple, but you could very well do that. And the last thing to talk about in today's slides, that's a list of what I consider to be useful matrix operations. So I've made this whole series before on my own private repository, or sorry, suppository, and I've noticed that a lot of the functions that I made I just didn't use. These are the ones that I used, and a few others. I'll get into those in a future video, but these are the core ones. And I can give you an example, a concrete example of how each one is used, and used many different ways. So the first one that's very important is being able to set all the values in a matrix to something, in particular 0. So basically just dropping in a quantity into every slot of a matrix. So we need that function. We're going to make that. I'm going to show you how it works. Then we have matrix set identity. That basically drops in diagonals for value 1, and then everywhere else is 0. That's very useful for linear algebra stuff. I have a function that I use called matrix populate. That basically goes into an array of structures, so like an array of some complex structure, and then pulls out, every couple of bytes, the quantities that you would want to drop into a matrix. That's an extremely useful thing to have when you're optimizing stuff and you're keeping record of all your iterations, and you want to pull values from each iteration and put them in a matrix. It's super useful to have a function like this that pulls values from the array of structures into your matrix, and then you can do further operations on that matrix. A couple more. Being able to insert and extract rows and columns is invaluable. So basically just dropping in a vector, either a row vector or a column vector, and then being able to pull that back out. Again, hugely valuable. Matrix transpose, infinitely valuable, just swapping elements across the diagonal. Great. Could also be used to go back and forth between row major and column major ordering, right? Couple more, add and subtract, basically adding matrices. This is basic stuff. In particular though, I want to talk about adding and subtracting them in place, which is just basically not using a third matrix. So here you can see I have like matrix A, B, and C. Well, I could just say A plus equals B and not have to worry about having a result matrix. If I don't want to carry A any longer, I could just increment A by B, right? Also, same thing for minus equals, right? Then I have matrix scale and scale in place. As you would expect, just multiplying a matrix, all the elements by a scalar quantity, very useful, as well as scaling in place, very useful. And lastly, perhaps the most important two operations are going to be matrix multiply, which is, what it says, just multiplying matrices. It's, again, extremely important in linear algebra. And then lastly, matrix copy, or I'm going to use memcopy because it's the same thing. We're just going to basically copy byte for byte a matrix from one address to another address. So yeah, that's pretty much it. Now let's get right into the code. Ignore my weird looking desktop, nothing serious, I promise. Okay, so let me show you I'm not gonna insult your intelligence here. I'm not gonna explain the code, it's so basic, it's like almost disrespectful to go through this. I'll just show you one. So here's my matrix add function. You can see it takes in a pointer to the result matrix, a pointer to the two source matrices that we're adding together, as well as number of elements, sorry, because again, if you're adding, you don't care about rows and columns, you just care about, hey, I'm adding every element, one for one in each matrix. And so here, these first couple instructions are me saving registers, the last few are me restoring registers, and then all it is a loop. I'm just looping through every element, copying from the two source matrices, adding them together, and then moving it to the result matrix, and that's it. That's pretty much how all these functions work. Add in place, extract column. I mean, as long as you understand the basics, you get this, so it's not really hugely important. The code's available, you can check it all out, public domain, everything is available for your usage, any purpose out there, so take a look if you're curious. I'm just going to show you how these functions are used, because again, the inner workings is so obvious. I'm not going to insult you with that. So let me see. So I have 4 examples. I have examples about creating a matrix. I have examples about manipulating a matrix, examples about basic arithmetic for matrices, and then also just in general multiplication. So let's open up the first example. Okay, so this, let me just run it first. I think that'd probably be the best idea. So this basically is just me creating a matrix in so many different ways. So initial matrix is, maybe I should just, this one I think I'm going to explain from the code before I show you this result. So the function I'm using for making a matrix, I'm using a few functions. I'm using set identity, I'm using set all values, I'm using matrix populate, and also mem copy. So all those different ways of making a matrix that I discussed previously, I'm going to show you how they function here. So the first thing that I'm doing is I'm setting a matrix. Well, I'm defining a matrix in memory. So back down here, you can see I've got a matrix defined here, matrix times 16 DQ 420. So that means I'm going to have a 4x4 matrix, and it's all going to be value 420.0. I'm also going to at some point have a matrix called another matrix, which I'm going to basically copy into the matrix called matrix, and that's going to use mem copy, obviously. That's defined to be 1.1, 2.2, 3.3, 4.4. I have a value called pi in memory, and I have this array of structures which encodes a bunch of random garbage. As an example, so it encodes animals basically. So the name of the animal, the number of legs, the approximate amount of hair, the height in feet and length in feet of the animal. So I've got cat, dog, bird, and bald man. So yeah, we're going to be obviously extracting data from this array of structures into a matrix. So I'll show you how that looks. So if I run this again, you can see the first matrix that we have right here. That's just the initial matrix. That was the 420s 4x4 matrix, just defined with the NASM DQ syntax. So 4x4 of 420. Then I've obviously used the set identity command to make that into a 4x4 identity matrix. And you can see that now that matrix is just 4x4 zeros and ones. Then I've used the set all values function to set the entire matrix to pi, so exactly 3.1. Fantastic. Then I've copied that another matrix into matrix, too many matrices. You can see I just mem copied that whole matrix here. That would be one way to make a matrix. And then lastly, remember I had that array of structures, I just pulled values. So this was the number of legs, this is the number of hair, this is the number of feet tall, and this is the number of feet long for, what was it, cat, dog, bird, and human. So yeah, different ways to make a matrix. They're all useful for our purposes in this series. Next example, example B. So let's see, this was, oh yeah, manipulating matrices. This is easy. So I'm just going to show you, I'm just going to run the code. I'm not going to even bother looking at the code. Let me clear everything and run that again. So our initial matrix, you can see, is just set to 0. So I've just defined that to be a 0 matrix at the beginning, and I have a row vector that's a, so our matrix is obviously a 4x3 matrix, and I've got a 1x3 row vector of just 7s, and I've got a 4x1 column vector of just, the number of the beast. So I can use a couple of those functions I talked about before. I can basically insert a row into a matrix. So here I'm inserting that row vector into row 2, or I guess the third row. So this is row 0, this is row 1, this is row 2. So you can see I've inserted that row in. That function is very useful. I have dropped in the column 666 into column 1. So you can see here I've taken that matrix again, I've dropped in that number of the beast down the column 1. And you can see I've got matrix transpose, so I've just taken that matrix and transposed it. So now I've got, instead of 6s down the vertical, I have across the horizontal, and now 7s are here and here as opposed to here and here, so we've transposed the matrix. Then we've got, remember we had those row extract and column extract functions. Here we can now pull rows and columns out. So here's now the 0th row of this matrix being pulled out, and here's the 0th column being pulled out. So All these functions are going to have uses in future videos. I just want to show you that we can implement them very simply in assembly. Okay, example C, basic matrix math. Again, I'm just going to run this. I'm not going to insult your intelligence by going through the assembly code here. So here you can see I've got some matrices. I'm just going to do some basic math with them. So matrix A is being defined as a 3 by 3 of 1s. Matrix B is a 3 by 3 of negative 2s. And matrix C is defined initially as a 3 by 3 matrix of 5. Here you can see I'm doing a scale in place operation of matrix C by 2. And you can see that that worked. Now we've taken out 5 matrix and now it's a 10 matrix. Next, I'm taking and doing this just the regular scale function. So I've got the matrix A and I'm scaling it by 3 and I'm storing it in matrix C. Again, useful function for linear algebra. So I'm taking this matrix, scaling it by, 3. So that's like a 1 matrix being multiplied by 3 and being stored in matrix C, which is all 3s. Great. Here I'm showing you the in-place add and subtract operations. So I'm taking matrix A and B and I'm incrementing them and decrementing them by C respectively. So remember, matrix A was all 1s, matrix B was all negative 2s, and matrix C at this point is all 3s. And so if I increment A by C, I get 4, and if I decrement B by 3, I get negative 5. That all works as intended. And then we have our regular add and subtract operations that are not in place. So here I'm taking A and B, adding them, and putting the value in another location, which is matrix C. Got all negative 1s, so here you can see matrix A was 4, matrix B was negative 5, so matrix C is all negative 1s when you add them together, obviously. And then if you subtract B from A and store it in C, you get all 9s, right? 4 minus negative 5 is 9. And lastly, if you multiply the current values of A and B, which last time I checked were 4s and negative 5s, you end up getting all negative 60s, right? Because 4 times negative 5 is negative 20, and there's 3 of them, so that's negative 60, and so, yeah, obviously that gives you that. And the last thing I wanted to show you was just non-square matrix multiplication, and that the algorithm that we have set up here works for that. And you can peruse the algorithm at your leisure. It's available in a suppository. So let's take a look. Let's take a look at the code actually, because it's probably so short, I might as well. So what I've got here, I'm pretty sure, yeah, I have a random. We had that random function that, remember, that pulled out a bunch of random floats for us into an array. Well, we can use that to test our code. So I'm taking that random array function and our matrix multiply function. I'm going to use those to show you that this function works. So basically what I'm doing is I'm generating a random, here you can see a 5 by 4 matrix using our random float array function from a previous video. And then I'm doing the same thing for a 4 by 6 matrix called B. Then obviously I'm going to multiply that A by B. So we're going to have a 5 by 4 matrix multiplied by a 4 by 6 matrix, and we're going to get a 5 by 6 matrix. So it's a bunch of non-square matrix multiplication. So this would be a good test. If this thing works with random numbers, that would be a good way to say, hey, our code works. And so yeah, that's what happens here. You can see we're just printing everything out, and we're going to call our matrix multiply function, and it's going to multiply A and B and store the value in C. So if I run this, here you can see I've populated this, what's it, a 5 by 4 matrix A with random numbers between negative 10 and 10. I'm populating matrix B, which is a 4 by 6 matrix with numbers between negative 10 and 10, and I'm multiplying them together. And we can test that this works. I can just grab basically all this. Let's open up Octave, and then let's paste this in. Oops. So let's see, does this match? And by the way, this is why I implemented our print array function in the way that I did, so I could just drop stuff into Octave to test. It's very useful. So you can see our matrix should look like on the top 11, negative 60, negative 60, 3, negative 29, and if you look, that's what it says. And let's check our last element here, negative 24, and we calculated it as negative 24. So obviously we did something right because our multiplication algorithm matches the one that the boomers made in octaves. So fantastic, we did it. We've done the basics of matrix math. All the code again is available in the suppository for you to take a look at. Not really groundbreaking stuff, to be honest, but it's just a precursor for future videos. If I had to cover this in the same video I was going to cover SVD or LU decomposition or something, it would have been way too much. So with that out of the way, I want to say thanks for watching. If you want to hang out, we have a Fed honeypot on the description, last link. Take a look, hang out with us. Have any questions? All the slides are available on the Discord, so yeah, check it out, and thanks for watching. See ya.